So an example we could use with our superheroes is going back to Spider-Man again. As he's swinging through a pendulum, we talked about the forces involved and had to worry about centripetal force and all the different components and different parts of our swing. What we can do with a pendulum is really just focus on where the mass starts and again where the mass ends and solve for anything in between. So let's start at the far end here with Spider-Man. At the far end, he's got gravitational energy. At the bottom, we know he's got his maximum kinetic energy, especially if we define the lowest point to be where there is no gravitational energy whatsoever. So we can solve for it anywhere in between. Or let's just go from start to finish. So going across our line here, we've got gravitational energy. That's going to turn into kinetic energy when we get near the bottom. So we've got the ball, Earth system. You want to talk about where the energy flows from? Flows from the Earth into the ball, giving the ball speed. So that should be an easy equation for us to set up. So we just set it up again as gravitational turns into kinetic. mgh turns into 1/2 mv squared. So we don't need the mass of the ball either, because it's on both sides of the equation there. So if I want to solve for the speed, I just got to do that 2 times gh square root. But the trick on a pendulum is this. What height does the pendulum rise to as it goes through that arc? Well, the good thing is gravity is path independent, so we don't care about how the ball got from its start point to its end point, just that it did get there. So really what we need to solve for is this height here. And what you can do is a little trick with the string. The string is length L, and whenever you pull it back, the string is still length L. So technically, if I can figure out how far the string is above this new horizontal, that will be how much height I've risen on the other side. The nice thing about the arc is that length is the same the whole time, but that highlighted piece, if I take this to be my angle, looks like it's the cosine. So it's L cosine of theta for that highlighted piece. If I want to solve for my height's going to be L minus L cosine of theta to give me my height. So as long as you know the angle that you've pulled back to and the length of the string, you're good to go. You've got height, and now you can solve for speed. Once you've got speeds and masses and gravities and heights and all that, you can calculate energies. And like we said before, the total energy of the system must stay the same. So if I've got gravitational energy totaling 15 joules at that moment, when I reach the bottom here and have kinetic energy, I know that this kinetic energy must add up to 15 joules just through conservation of energy. If I picked a location anywhere in between here, I know that the total energy of that point must be 15 joules. So let's say that my gravitational has dropped to 6 joules. That kinetic energy is turned into 9 joules. And from just that conservation of energy, I'll be able to pull out what the speed was or the height was, depending on whatever information you might be given. So that's the trick with pendulums. Let's look at another scenario. In this scenario here, we've got someone jumping off a bridge with the bungee cord on. So when the person is free falling, we can analyze their energy at several different points here to figure out how far the bungee cord is stretched, figure out how fast they're going, where their maximum speed is. Those are all little things that we can focus on. So we'll have 4 different locations here. We'll have location A when they are on the bridge, location B when the bungee cord gets to its unstretched length. Over here, C looks like we've reached a certain length due to our stretch, and D will take to be the entire height of the bridge. So the water is just below the person's head. People do this and try to just touch the water and come back up. Better make sure you know all the information about that bungee cord before you do this jump. So let's set up energy equations A, B, C, and D, and I'll do it all on one LOL for you. Alright, so we're going to go from position A to B. From position A to B, I know that I've got gravitational energy due to my height. At the top of the bridge, you're not moving, so we're at rest. The spring has not been stretched yet, and we won't worry about any of those non-conservative forces. Over here, you're going to have Earth, spring, and person. So when I get to location B, I'm moving quickly. In terms of gravitational energy, in terms of height, if you want to make the height 0 to be the ground, I still have some gravitational energy at that point. And over here, the spring has not been stretched yet. So from location A to location B, our energy goes from gravitational to less gravitational and now some kinetic. So now let's look at location A to C. So again, in the beginning, nothing's changing. I'm still some height above the ground. But now, when I get to location C, I know that the spring has become stretched. The gravitational energy is much less. And I've got some kinetic energy here. So you've got actually all three energies on the right side of your equation. And you're starting with just one. So if we go back and look at that scenario, one of the big questions is, where is the bungee jumper's maximum speed? When are they going as fast as possible? It could be at location B or location C. Take a guess, think about it, and then we'll talk about them. Watching these people bungee jump, they're freely falling now. And remember that force in the spring does not kick in until they get to the unstretched length. Right now is when the drag force or the spring force is kicking in. Watching it one more time, let's notice the point when the speed is max. There's when the force starts, and that's when they reach the bottom. Alright, so in the picture here you can see that location B has a much bigger velocity area than location C. Just from the picture, you would say, yeah, B would be where you're moving as fast as possible, because the spring isn't stretched yet, so all your gravitational energy is turning into speed energy. Okay, but you are forgetting that there is a height at that point. I would make my height 0, probably the ground, and so I still have gravitational energy and kinetic energy at that point. Could it be location C? With location C, you've now got energy in the spring, so there's no way that could be your fastest point. But I called you to look at the forces on the person at B and C. At location B, the spring is not stretched yet, so the only force I see on it is gravity. So you will continually pick up speed as you reach the ground. At location C, to go from B to C, gravity is still pulling down, but that spring force is starting to grow. And if you look at that, all the way until you get to the point of C, the spring force and the gravitational force aren't equal yet. And if you look at how they're unequal, I still have more force down. If I have more force down, that means I'm going to continue to accelerate down. So the spring force is growing, kind of like a drag force on you, and you will be at maximum speed when those two equal each other. So when the spring force equals the gravitational force, that's when you're at max speed. After that point, as you move from C down to D, the spring force gets even larger as your gravitational force stays the same. So really, C is where you're moving maximum speed, when the spring force matches gravity and those two are equal. If I go back and do my LOL for location D, so over here we start with gravitational energy at the start. When we reach the final stretch in the spring, we're out of speed, we're out of height, and now everything is in spring potential energy. So you're moving from one form to another, and again, we know how to set those up and solve for those. In this last example here, what we're trying to see is how far does this box slide up the ramp before it comes to a stop. And what I'm going to do is I'm going to throw in some friction to this problem to make this a little bit more complicated. Obviously, without friction, you can reach a lot higher height because all your kinetic energy at the bottom can turn into gravitational potential at the top. But with friction around, you're going to go to a lower height. So let's see how we can set this up. Let's write down what givens we have. So here's what we know. We know the mass, we know the coefficient of kinetic friction here, we know the initial velocity, and the angle of the hill. So in looking at this, let's go back to one of our energy bar graphs and set this problem up. So at the beginning of this problem, we have kinetic energy. That box is sliding up the hill. It's on the ground at the beginning, so there's no height potential energy. There's no spring potential. There is work going to be done by friction here. So I'm going to put that down in the negative region since the hill is going to take some of my energy away, and there's no external forces from someone pushing outside the system. Over here at the end, when we reach the highest point, we will stop moving. So our kinetic will be 0. We'll have some new height and gravitational energy, but we won't have any spring potential energy written out. So our system is the box, earth, and ramp. And what we're going to see here is that some of the energy is going to go into gravitational energy from the box, and some of it's going to go straight into the ramp, making the ramp a little bit warmer as we go along. So I can already see how my equation is going to set itself up. Let's set that equation up. So I've got the kinetic energy minus the work done by friction equals gravitational energy. We know how to calculate these things. So there's how we set that up. If we want to calculate that force of friction, you have to look at and analyze the hill. We know that our forces, our gravity, our normal force, and our frictional force. So our frictional force is fighting us as we go up the hill. So the force of friction is going to be the coefficient of friction multiplied by what the normal force is, and the normal force is in line with this part of our gravity. So it looks like the cosine of our gravity. So really, this will be mg cosine of theta multiplied by the displacement. So that's how we can get the work done by friction as we go along here. If you look, there's a mass in every single spot. And we've got a height and an x value. Now one thing we want to know is how far up the ramp, so we're just looking for the x value. So what you're going to have to do is get rid of this height and use that height in terms of distance traveled. So if we're looking for displacement here, it looks like displacement is the hypotenuse and the height is the opposite side of the triangle. So height, we can rewrite that, and height now becomes. So now you should have everything that you need for the problem. You should have the starting speed, the coefficient of friction, the angle of the hill, and that's all we really need to solve for our displacement. If you solve for your displacement, you should end up with around 2.05 meters. So hopefully these example problems will help you set up and work through the problems that you're going to have in your homework. Good luck. If you have questions, let me know.